Hello and welcome to this video on the ICND2 series. In this video, we are talking about spanning tree, and so we're going to define spanning tree. We're also going to look at the root bridge selection process, and finally we're going to look at the port roles in spanning tree. So let's get started. So what is spanning tree? Spanning tree is a loop prevention mechanism that is introduced to ensure redundancy in switches and to prevent broadcast terms. Now let's just explain what that means. So for instance, if we have switch 1, switch 2, switch 3, and switch 4. Now, if you have internet that is connected to switch 1, so this is 1, 2, 3, and 4. And if you have the internet which is connected to switch 1. Now, for switch 2 to go to the internet, it has to be connected to switch 1. So for switch 3 to get to the internet, it needs a connection to switch 1. And for switch 4 to go to the internet, you can either go through switch 2 or switch 3, or go to switch 1 directly. Now, but what happens when one of these switches loses their link? Like for instance, if this link goes down, an option would be for switch 2 to come through switch 4 and to go to switch 1. Now, once you have this, you have a condition where there's a potential loop because you can have packets going from switch 1 to switch 2, back to switch 1, then switch 2 to switch 4, back to switch 1. So the broadcast is sent from switch 3 to go through to switch 1 to switch 2 to switch 4 and then loop between switch 1, 2, and 4 every time because all the ports are forwarded at the same time. So what spanning tree does is to make sure despite the inter-switch links, there are only a few ports are forwarding at the same time, and that sort prevent links. So with the spanning tree, what we can see is that this link will always be blocked, and only these three will work until it gets to a point where one of the links goes down. So that way, we can ensure redundancy without sacrificing the network, and that's what spanning tree is about. So spanning tree actually uses what is called BPDUs, and that's Bridge Protocol Data Units. So how it works is that each of the switches, they send information via these BPDUs, and it's based on this information that spanning tree occurs. So basically, there are 3 steps in spanning tree. The first one is that what's called a root bridge selector. So pretty much the root bridge is a root of the network. It's a part of the network where all traffic will go through. So what happens is that all the switches, they go into an election and they select one person and say, this is going to be our root bridge. And based on that root bridge, that's where all of them would send traffic. So for instance, switch 4 is the root bridge. What's going to happen is that for switch 3 to send any traffic, it's going to first send it to switch 4, and then switch 4 will forward the rest. So for instance, if switch 2 wants to send traffic to switch 1, it's going to first send it to switch 4, and then send it to switch 1. So that's how the root bridge works. And then after that, they select what's called the root ports. And basically, the root port on the switch is the port that has the shortest path to the root bridge. We'll explain that in more detail. After a root port is selected, designated ports are also selected. And designated ports are port segments while the root port is for switch. So every switch has its one root port. For every segment, that's like every link. So this link would have a designated port. This link would have a designated port. So designated ports are per link, while root port is per switch. And that's the difference. And finally, block all of the ports. So there are just 3 steps in spanning tree. First is to select the root bridge, second, select the root port and designated port, and third one is to block all the other ports. So that's how spanning tree works. Now let's go into more detail and look at the root bridge and the root ports. So we have a network of, say, 4 switches. So switch 1, switch 2, 3, and 4. Now let's assume they are connected this way. In selecting the root bridge, what's going to happen is that each of the switches would send out its BPDUs. And each switch has what is called a bridge ID. So the switch that gets the bridge route is the switch that actually has the lowest bridge ID. Now, what is the bridge ID of the switch? The bridge ID is an identifier that is made up of 2 components. It's actually the bridge priority plus the MAC address. And what is the bridge priority? The bridge priority is just a number between 0 and 65,536. So switches with a lower bridge priority are more likely to become the root bridge than switches with a higher bridge priority. So what happens is by default, the priority of everybody is this 32768. So by default, you can have switch 1, switch 2, switch 3, and switch 4 having 32.768 as their priority. Now, every switch is using a priority as a default priority. Then we're going to use the MAC address to break the tie. So in that case, it's the switch with the lowest MAC address that becomes a root bridge. So for instance, if the MAC address of this switch is 1111.1111.1111, and this switch is 2222.2222.2222. Now don't forget that these numbers are hexadecimal numbers, and this switch is 3333, and this one is 4444.4444.4444. Now because switch 1 has the lowest MAC address, it's going to become the root bridge. All the remaining switches in the topology would start sending traffic through switch 1. Now why is this important? It's important because the root bridge of the topology should be the switch with the most capacity, the switch that is central to the network. So for instance, if you are designing networks, we have what is called the access layer, the distribution layer, the core layer. So at the access layer, we have the wiring closest to where we have many switches, and they're all aggregated to what is called a distribution switch. And then you have many distribution switches. They're also aggregated to a core switch. Now you can have more than one core switch, maybe for redundancy and things like that. So you can have this and then many access switches here, and then they're all connected to the distribution switches. I'm sure you get the picture. Now, if you really want to be able to reach one of the switches, maybe because it has the lowest MAC address, that means that for any of the switches to send traffic to another switch, so imagine the switch wants to send traffic to this switch. We're actually going to try to go through this switch here, so we're going to have traffic flowing this way, and maybe this way, and then this way, and then coming down the root bridge before it comes back up, and then goes this way, and this way, down this way. So it's a really messy way to send traffic. So the best thing to do is to make sure that the core switch, which is at the center of the network, is actually what becomes a root bridge. And also from a processing capacity, you can have access switches there like maybe 2960s or 3750s, which are Cisco's low-end switches. And you can have distribution switches that are probably 4500s, and core switches that are like 6500s or things like that. So you can see that the capacity of the switches are actually increasing as it goes from access to distribution to core. If you actually design a network, you should make sure that the root bridges are the core switch, which has more capacity and which is more central to the network than any other switch in any closet, because that design is going to be more efficient. So if we want somebody else to become the root bridge, I don't want to leave it a chance. The best thing to do is to go into the switch and change the priority of the switch. So it's very easy. What I could do is just come to this switch and change the priority to maybe 4096. And then assuming the rest are on their default priorities, then 4906 is going to be way less than 32768. Because of that, that's going to become the root. So that's how we influence root bridge selection. Now let's move on to the port roles and determine the root ports and the designated ports. Now I'm just going to redraw the network we had before. Now we select switch 1 as a root bridge, which is not so terrible assuming that they have the same capacity because it's central to the network and has connections to all the other switches. Now how do we determine what the root ports are for each of the switches? The root ports for each of the switches are the ports that have the shortest path to the root bridge. So in this case, assuming all the links are 1 gigabyte links, then according to the spanning tree, they're all going to have a cost of 4. So what's going to happen is that switch 2, switch 3, and switch 4 will determine the shortest path to get to the root bridge. So switch 3 has any one path to the root bridge, which is this path, so it's going to make this port the root port. For switch 4, this is going to be the root port. For switch 4, it has 2 paths, one directly to the root bridge and one to switch 2. The one directly to the root bridge has a cost of 4, while the one through switch 2 has a cost of 4 plus 4, which is going to be 8. So it's going to pick the one with the lowest cost. So this is going to become root port. So after selecting all the root ports, the next thing to do is to select designated ports. And then designated ports are actually selected up a link, and they're always the closest to the root bridge. So for instance, all the ports on the root bridge are automatically designated ports. So we're going to have the designated port here, the designated port here, another designated port here, because by default, they're connected to the root bridge, and so they're going to be the closest to the root bridge. Meanwhile, on this segment, We don't have any designated port yet. So we're going to try to choose a designated port between switch 2 and switch 4. And when you look at switch 2 and switch 4, the closest one to the root bridge is switch 2. So the closest is going to be the designated port. And then this port's going to be the left, and we're just going to block it. Now, this is a little easy, so let's assume we have another switch 5 here. And I can have it go through this or through this. So switch 5 has 2 links, one through switch 3 and the other through switch 4. Now, to determine the root port here, what we're going to do is to say, you can either go through this one on a cost of 4 plus 4, which is 8, or go through this one on a cost of 4 plus 4, which is also 8. So there's a tie here. So we're going to go to the next criteria, which is the upstream bridge ID. So we're going to check in switch 3 and switch 4, which one has a lower bridge ID. Because they're all using the same default, which is 32768 for the priority, they're going to break the tie with the MAC address. And because the MAC address for switch 3 is 3333.3333, while switch 4 is 4444.4444, then switch 3 is going to win, and so this is going to become the root port. Now again, we need to find designated ports. Here, this is going to be the designated port because obviously it's the closest to the bridge, while on the path between 4 and 5, this is going to be the designated port. Now what if we have switch 6? And switch 6 has 2 links connected to switch 5. In that case, switch 6 also has to select a root port. But for each of the links, assuming they have the same bandwidth, the lowest cost the same. The upstream bridge ID is switch 5, so it's the same. So the next thing to use is what's called the port priority. The port priority is just like a bridge ID, but the number between 1 and 256. And default is 128. So assuming these 2 ports are using the default, the next thing to break the tie would be the lowest upstream port number. And in that case, if this is fast Ethernet 0/1 and this is fast Ethernet 0/2, because this is lower than fast 0/2, this will become the root port. So eventually this will become the designated port when you are selecting designated port, and this will also become a designated port. So this link would be blocked. So we have this link blocked, we have this link blocked, and we have this other link blocked. And once the edge of a link is blocked, technically that whole link is blocked. So we have to reduce the topology. We're going to have switch 1 connected to switch 2, connected to switch 3, and switch 4. And the links that we're going to have active would be this link, and this link. And then we just connect it to switch 5, which is connected to switch 6. So despite the fact that we have redundant connections that are here, and here, and another one here, those redundant connections are not going to be used once the link goes down. So despite the fact that we have redundant connections across the whole topology, those redundant connections would not be used until a link goes down and the spanning tree algorithm is calculated again to determine the ports that would either be in the forward mode or in the block mode. So the root ports will be forwarding. The designated ports will be forwarding. So these are the 3 different port roles and how they affect spanning tree and how they help to prevent loops. Because with this topology, even if a broadcast is sent from anywhere on the network, you're not going to have a loop because all the redundant parts have been blocked. So let's just get familiar with different priorities and costs that we have in spanning tree. So for the interface cost that helps determine how far away we are from the root bridge is dependent on the bandwidth. In the table here, we have a 4 megabit bandwidth. The cost is $250. You have something like 100 meg, the cost is $19. You have 1 gig, cost is $4. If you have 2 gig, cost is $3. You have 10 gig, the cost is $2. So if switch A is connected to switch B on a 1 gig link, switch C is connected to switch B on a 1 gig link. So for some reason, switch A is connected to switch C on a 100 meg link. In this case, if switch A is a root, switch C would prefer to get to the root bridge to switch B, and then they go directly because the shortest would be 4 plus 4, which is 8, versus going through the 100 meg, which is 19. So it's going to actually pick this link over the link that goes directly. So that's one case where you need to be familiar with the cost. That thing is for the bridge priority. We already talked about it. It's from 0 to 65,536. But there is a catch here. It can only be multiples of 4,096. So essentially, it's because it's a 4-bit number. And there are actually only 16 different values that you can have. So it actually goes from 4096 to 8192, and it goes in increments of 4096 like that. So you can actually have a bridge party that's 4100 or things like that. It just wouldn't work because that's not how it works. The next thing you should know is that the port priority 2 is a number from 0 to 256, and it's multiples of 16. So you can have port priority 16, 32, 48, but you can't have a port priority that is 12 or 17. Again, this is because it's a 4-bit number. And so they only view 16 values, but it can be a number between 0 and 256. So in this video, we've been able to look at what spanning tree is and why we have spanning tree. We've also been able to look at the spanning tree process, which is about selecting the root bridge, determining the root ports and designated ports, and blocking out the other ports. And we've been able to look at how to select our root bridge and different port roles that we have in spanning tree. Thank you very much for watching. Hello and welcome to this video on the ICND2 series. In this video, we will continue talking about the spanning tree protocol. So in the last video, we talked about the spanning tree protocol and the port roles and the root bridge selection and things like that. In this video, we are going to look at the spanning tree port states. We're also going to look at rapid spanning tree. We're going to wrap up by looking at the per VLAN spanning tree protocol. So let's get started. With 802.1d. 802.1d. There are 5 spanning tree port states. So you have disabled, and that means that the administrator has turned off spanning tree on the ports. You have blocking, and blocking is when the port is being blocked. So when you've gone through the spanning tree port mode and their remaining ports will be block ports, so they are in blocking mode. Then we have listening mode, we have learning mode, and we have forwarding mode. Now what happens is before any ports can go into the forwarding mode, it has to go through the listening mode, where it's just listening for BPDUs to determine if it's supposed to go through into forwarding mode or if they're actually better BPDUs and they're supposed to stay in the block mode. We also have the learning mode, and in the learning mode what happens is that the switch is learning about MAC addresses. So remember how we talked about MAC addresses in the ICND1 and how the switch learns MAC addresses using the source MAC address. So before a port can start forwarding, in order for a switch not to act like a hub, it has to build its MAC address table, or it's called a CAM. And the CAM means the context addressable memory. And so the switch dedicates some time into learning MAC addresses before it moves into forwarding mode, where it can start forwarding traffic. So it spends actually 15 seconds in the listening mode and 15 seconds in the learning mode before it goes into the forwarding mode. And it can spend up to 20 seconds in blocking mode. So if it switches being blocked before time expires, it might get up to 20 seconds. So what happens is if a port is supposed to go from blocking to forwarding, it can spend up to 50 seconds. That's 15 plus 15 plus 20. But this is going to spend a minimum of 30 seconds in the listening and learning mode before it gets to the forwarding mode. Now take, for instance, if we have a network with switch 1, switch 2, switch 3, and switch 4, and we have the links, and after the spanning tree, we desire to block this port, for instance. If for any reason this port goes down, and we need to bring this port back up, we're going to spend between 30 and 50 seconds trying to bring up the port. It takes a lot of time, so the network is usually slow. Because when spanning tree was designed, back in the days when 802.1d was designed, 1 minute was not a long time for a network to be down. If you have many hosts that are connected to the network, and you have the same thing where the host is connected to the network, they also go through the 30 to 50 second delay before they can actually join the network. But now that causes a lot of problems because hosts can boot up in less than 30 seconds. And so you have computers that have boot up and they can, for instance, receive a DCHP address, or they can't join the domain. Because of that, you have computers that cannot connect to the network because the switches are too slow because they're going through listening, learning, and forwarding modes. So what Cisco has decided to do is to go through some improvements, and some of the improvements include something that's called PortFast. What PortFast does is that ports that are directly connected to hosts can go directly from blocking mode to forwarding mode without going through listening and learning. So they can start forwarding packets immediately. And that way, the network convergence time is really reduced because they don't have to go through 30 seconds of listening and learning. And that's fine because ports that are connected to hosts cannot cause loops. In fact, if you're trying to configure port fast on a switch, you're going to see an error like this command should only be done on ports that are connected directly to the host. Don't do that on trunks and ports that are connected to other switches because they can cause loops if it doesn't go through the listening and learning stage. Now, apart from port fast, there are other Cisco technologies that have been introduced to make switches converge faster. Another one is called uplink fast. And there's something else called backbone fast. And although this technology is under the ICND2 curriculum, there are Cisco proprietary features that were introduced to make the convergence time faster, even before the IEEE standard for better spanning tree came out, which we will discuss in a second. And as we go ahead in this series, we're going to see cases where Cisco had to develop technology just because they are leaders in network equipment manufacturing and they have to be constantly innovative about their products. So we've had cases where even before the technology comes out, Cisco's created a technology that finally becomes standardized. It's happened to many other technologies like HSRP. So let's just move on to rapid spanning tree. We already established that spanning tree protocol is too slow because of the 50-second delay. And we said that Cisco created port fast and backbone fast and uplink fast to solve that problem. But the problem was that all these technologies were Cisco proprietary, so they don't integrate with other vendors. For instance, if you have a network that has Cisco switches and other switches, you cannot use all these technologies to integrate with other switches. So because of that, IEEE developed a new spanning tree protocol that is called the Rapid Spanning Tree Protocol, and that's the 802.1w. The original spanning tree protocol was 802.1d. And pretty much what spanning tree protocol does is that it's a lot more proxy and faster than the regular spanning tree protocol. So I'm just going to give an example. So assuming switch 1 is the root bridge, and then we have this port being blocked and this port being blocked after spanning tree has converged. Now, if for any reason we introduce a new link, for instance, this link coming from switch 1 to switch 5, so now it's a direct link from switch 1 to switch 5, which makes it a better link for switch 1 to get to switch 5. If it were the original spanning tree protocol, before this link could be used as a root port, it's going to take 50 seconds, which is a lot of time to converge. But with the rapid spanning tree, what happens is that switch 1 is going to send a BPDU to switch 5, which is going to be superior to what's called a superior BPDU to the BPDU that switch 3 sends to switch 5. And the moment it sends to switch 5, it's like a proposal. It's going to block that port. And the switch 5 is going to receive it and process it and compare it to the BPDUs that it receives from switch 3 and switch 4. And it's going to see that it's really superior. What it's going to do is it's going to agree. So it's going to send an agreement message back to switch 1. And immediately switch 1 is going to unblock the port. And then this will become its root port. So what happens is switch 5 is also going to send out BPDUs to switch 3 and switch 4, trying to tell them to go through it to get to the root bridge. So it's going to send out BPDUs to them, and at the same time, it's going to block the ports. And then they are going to check and again say no, that we have a direct connection to reach the root bridge. So we're not going to use your own BPDUs, and we're not going to go through you to get to the root bridge. So what happens is that the network will still be converged because at the end, this would no longer be a root port. We're going to have these two links being blocked, and this link will still be blocked, but less than 50 seconds. In fact, about 2 to 3 seconds. The better link will start being used, and the faster link will start being used because of the whole proposal and agreement kind of negotiation process with Rapid Spanning Tree Protocol. Now, there are some other things you need to know about Spanning Tree Protocol. It's like instead of having 5 states of the original Spanning Tree Protocol, we just have 3 states, and that's discarding, learning, and forwarding. So a port's either discarding or learning or forwarding, so we don't have listening states or blocking states. Whether it's blocking or listening, it doesn't matter, just discarding packets. And then it can be learning and it can be forwarding. So technically, all the Cisco features like the backbone fast, uplink fast, they've already been adapted into Rapid Spanning Tree. So instead of configuring backbone fast and uplink fast in your network, you can just deploy the Rapid Spanning Tree protocol. Now, before we conclude on spanning tree, we're going to look at one more type of spanning tree protocol, which is the per VLAN spanning tree protocol. Now, so far, the kinds of spanning tree protocol that we've been talking about have been spanning tree protocols that span switches. So what we have is different switches, regardless of the number of VLANs that we have on the switches. We just elect one root bridge. So what happens is that you have a connection like this. You find out that you may never use this link. Where we keep sending traffic out all these three links. And it might get to a point where this link may be saturated, but this link will always be unused. Now, it may seem simple when you're at it from a network of 4 switches, but consider a network with by 100 switches, and then you have 2 core switches, and you have different distribution switches connected to the core switches, and then you have access switches below. Now, these kind of designs, if you run spanning tree protocol, we're going to have a lot of ports being blocked. And so we can have these ports being blocked. We'll have one of these ports being blocked. We're going to have like this port being blocked and so many ports being blocked. And so we're going to have many unused links. So if we're running just one instance of spanning tree protocol, what that means is that we're going to have unused links and our second core switch will not be really utilized. And so we're going to have inefficient use of resources because we're going to creating this link and having these fiber cables run and buying switches, and for the most part they're not going to be used because something has gone wrong with the network. So the way to fix this is to use what is called per VLAN spanning tree protocol. What happens is that for each VLAN you have a different instance of spanning tree with a different root bridge. So if I have 5 VLANs, for instance, I can say for VLAN 1, 3, and 5, this is going to be the root bridge, and for VLANs 2 and 4, this is going to be the root bridge. So that way we get to have redundant links. So for a particular VLAN, this might be a blocked port, while for instance, for VLANs 1, 3, and 5, this might be blocked, while for VLANs 2 and 4, this is actually going to be permitted. So what actually happens is we have flexibility and efficiency, and if something goes wrong, we can still have our redundancy because the ports that are being blocked for a particular VLAN can now become forwarding ports for the other VLAN. And so those ports can now carry all the traffic. So for instance, if a particular port goes down, if this port goes down, we can have this port carrying traffic for VLANs 1, 2, 3, 4, and 5. So that makes it a lot more efficient. So you're going to have different root bridges, different root ports, different designated ports, different block ports per VLAN. So technically what happens is the root selection process is the same. Everything is the same. But what we can do is that for each VLAN, we can influence the selection process. So I can go into a switch and say, for VLAN 1, your priority is going to be 4096. And while for you, for VLAN 2, the priority will be 4096. This is going to be the root bridge for VLAN 2. While this is going to be the root bridge for VLAN 1. Now, per VLAN spanning tree actually uses ISL. In the sense that it's only supported by ISL because of the way it was designed. Per VLAN information is actually encapsulated in the ISL header. And so 802.1q switches could not use per VLAN spanning tree. So why 802.1q began to gain a lot of popularity in Cisco devices and ISL was being deprecated. Cisco actually went back to create what's called PVST Plus. And PVST Plus is just PVST. They now support 802.1q, or they're now supported by 802.1q. And that's actually the default spanning tree protocol that you have on Cisco devices. It's per VLAN spanning tree plus, meaning that it can actually be backward compatible with the regular spanning tree. It can be compatible with non-Cisco devices because it supports 802.1q. And still, it allows you to have one spanning tree instance per VLAN, which makes it a really good protocol. And then we can also combine per VLAN spanning tree protocol with rapid spanning tree protocol, and we have what is called rapid per VLAN spanning tree protocol. So what happens is that it's just going to be the rapid spanning tree protocol, which makes it a lot faster, and then you still have one instance of spanning tree per VLAN. So it actually have rapid per VLAN spanning tree protocol. So there's the variances of the original spanning tree protocol that are designed by Cisco to make it a lot faster and a lot more efficient. So in this video, we started off by looking at spanning tree port states and the 5 spanning tree port states that we have. We went on to look at the rapid spanning tree protocol, and we concluded by looking at the per VLAN spanning tree protocol. In the next video, we're going to go to the command line. We're going to see how spanning tree protocol works. Everything is turned on by default, and we can change a few parameters to see how it affects the spanning tree configuration. Thank you very much for watching. Hello and welcome to this video on the ICND2 series. In this video, we will look at spanning tree configuration. So we're going to look at how to configure spanning tree, how to verify spanning tree, and how the root ports and the root bridge are selected on the command line. So we're going to be spending most of our time on the command line. So we have switch 1, which is connected to switch 2. Which is connected to switch 3. Switch 1 is also connected to switch 3. So switch 1 is connected to switch 2 on fast port Ethernet 0/13. So that's fast Ethernet 0/13. And switch 2 is connected to switch 3 on port fast Ethernet 0/16. Fast Ethernet 0/16 and fast Ethernet 0/16. And switch 1's fast Ethernet 0/16 is connected to switch 2's fast Ethernet 0/13. So we're going to head off the command line and see how spanning tree works in the command line. So we're on switch 1 right now. And what we're going to do is go into the privileged mode and we're going to say enable. The first thing we're going to do is to show the sleepy neighbors. So show sleepy neighbors. And then sleepy neighbors shows just the devices that are directly connected to us. In this case, switch 2 and switch 3. So we have switch 2 connected on fast Ethernet 0/13 and switch 3 connected on fast Ethernet 0/16. So we're going to go right into spanning tree and we're going to start by verifying because spanning tree is configured by default. So we're going to check what modes the spanning tree is running. So we're going to say show spanning tree. And we can see right now it says it's going to default IEEE spanning tree protocol. And we can see that it's saying that the root ID is this particular MAC address, and its own MAC address is 001F.6094.7B80. So this switch is not a root switch. We can see why it's not a root switch. Even though the priorities are the same, they're both at 32769, which is just 32768, which is the default, and the VLAN number, which is 1. So that's the 32768 plus 1, which is 32769. But we can see that the MAC address of this bridge is higher because it starts with 001F. While the other one is 000F. So we don't know which switch is the root bridge, but we know it's not switch 1. We can also see that fast Ethernet 0/13 is the one that's in the blocking state, while fast Ethernet 0/16 is the one that's in the forwarding state. And the reason for that is because fast Ethernet 0/16 is the root port. So if we go back and do show CDP enable, we can see that fast Ethernet 0/16 connects to switch 3. And so because of that, and that means that switch 3 should be our root bridge. So we're going to go to switch over to switch 3 and trying to find out. So we're going to go to switch 3 now. And we're going to show spanning tree. And sure enough, we can see that this bridge is the root. So this is the root bridge and this is the MAC address of the root bridge. And of course, the 2 ports on the root bridge are both designated ports because we know that all the ports on the root bridge will be designated ports. So if we go back to switch 2, so we just go to privilege mode, it shows spanning tree, and yeah, we can see that fast Ethernet 0/13 and fast Ethernet 0/16 are both in forwarding mode, but the fast Ethernet 0/13 is a designated port, and we show CDP enable. We're going to see that the fast Ethernet 0/13 connects to switch 1. We can see that fast Ethernet 0/13 connects to switch 1. Now we don't need fast Ethernet 0/24. In fact, I'm just going to shut it down. So CompT interface space fast Ethernet 0/24. This is going to shut down. Now if we go back to our network diagram, we will see that switch 3 is the root. So this is the root bridge. We also have been able to see that these ports are designated ports. This is a designated port, and of course, this is the root port, and this is the root port. This is the designated port, while this is the blocked port. So right now, because switch 3 is a root bridge, the link between switch 1 and switch 2 is not being used, so this link is actually down. So what's going to happen is if we create VLANs 2 and 3 on each of the switches, we're going to have VLANs 1, 2, and 3. And let's see how spanning tree is going to work on the switches. So I'm just going to go to each of the switch and create VLANs 2 and 3, and then we're going to look at what spanning tree does. So I'm going to go back to command line now and create VLANs. So I'm switch 1 right now, and I'm going to say VLAN 2 and 3. And just going to exit. We're going to do that in switch 3 and switch 2 also. So on switch 2 config mode now. And switch 3, I'm going to do the same thing. So show spanning tree. Now we can see that for each instance of spanning tree, we actually have a root bridge. But switch 3 is still the root bridge for all the 3 instances of spanning tree. So for VLAN 1, we have this bridge as a root. For VLAN 2, we have this bridge as a root. And for VLAN 3, we have that this bridge as a root. So what we're going to try to do is make switch 1 the root for VLAN 1, switch 2 the root for VLAN 2, switch 3 the root for VLAN 3. So we're going to go to switch 1. How we're going to do that is that we're going to make it a root for VLAN 1. And the easiest way to do that is use command spanning tree. We're going to say VLAN 1. We're going to say make it the root. So spanning tree VLAN 1 root. Well, we're going to say is the primary root. Cisco allows you to have what is called a secondary root, but what it really does is for secondary root is it makes a priority higher than that of the primary root, but lower than the default, which is 32.768. So that if the primary root goes down, the switch with the next priority, which is a secondary root, become the root switch. So we're going to go to switch 2, and we're going to make it the root, so we can say exit and say spanning tree VLAN 2 root primary. We know that switch 3 is only the root for VLAN 3, but we're also going to go to switch 3 and still use a command and say conft spanning tree VLAN 3 root primary. So not show spanning tree here. And we can see that for VLAN 1, it's no longer the root, but the root is this MAC address, which is switch 1's MAC address. We can also see that for VLAN 2, it's still not the root, but the root is this MAC address, which is switch 2 MAC address. And for VLAN 3, it is the root. So if we go to switch 1, if we do show spanning tree, we can see that for VLAN 1, it is the root bridge. It says this bridge is the root. And all these ports are designated ports. For VLAN 2, it's not the root bridge, but the root bridge is the address of switch 2. And we can see that it has one port blocking fast Ethernet 0/16 is blocking on VLAN 2. And if we go to VLAN 3, we can see that it's also not the root bridge, and it has fast Ethernet 0/13 has blocking on VLAN 3. So if we go to switch 2, we show spanning tree. We can see that switch 2 has fast Ethernet 0/16 has blocking on VLAN 1. It's not the root, but it's the root of VLAN 2. It's the root bridge. It says this bridge is the root. And for VLAN 3, it's not the root. So if we go back to our topology, we can see that for VLAN 1, we have this link has blocking because switch 2 is blocking fast Ethernet 0/16. So this is blocked for VLAN 1. For VLAN 2, we have switch 1 blocking fast Ethernet 0/16. So this link is blocked for VLAN 2. And for VLAN 3, we have fast Ethernet 0/13 on switch 1 being blocked. So we have this link blocked for VLAN 3. So because we have the root switch on 3 different switches for the 3 different VLANs, we verified that we're not just blocking one link, but on VLAN 1, this link and this link are being used while this is being blocked. On VLAN 2, this link and this link have been used while this link is being blocked. While on VLAN 3, this link and this link have been used while this link is being blocked. So every link is being used for 2 VLANs while it's being blocked on a third VLAN, which makes it more efficient, and that's why per VLAN spanning tree protocol is more efficient. If we go back to any of the switches and do a show run, we're going to see that we're actually running the spanning tree mode PVST, which is per VLAN spanning tree protocol. And we can see that the priority for VLAN 2, because this is switch 2, has been reduced because we put it in the command spanning tree VLAN 2 root. So it has reduced the priority so that it can become the root bridge for VLAN 2. So pretty much that's how the spanning tree protocol works. And this is how PVST works. So when you have different VLANs on Cisco switches, you can configure the root bridge to be different for different VLANs. So you can utilize more links. In the next video, we're going to look at how to bond 2 ports together using what's called Ether channels. Thank you very much for watching.